Okay. In this particular problem, we can note that it's symmetrical. There's symmetry about the middle line here. If we draw a line straight down the center, there would be, we notice that essentially it's the same things happening on the left as the right of that. Okay. Now, due to the symmetry, that helps us in a couple of cases here. One of the things is that what we recognize right off the bat, that we have 40 kNewtons going down, acting down on this truss structure. And due to symmetry, what that would mean is we'd have 20 going up here and 20 going up here. So it's easy just to interpret it directly and say that it's going to be 20 kNewtons going up and 20 kNewtons over here. Okay? And that's essentially what the author does here, draws the first diagram showing that it's 20 kNewtons up. Okay? Now the next thing we can see here is that we have 2 meters on one side and 2 meters on the other side. So we have essentially a triangle that has the adjacent side and the opposite side are equal. Okay, so each one of these, it doesn't matter if you do the whole thing all the way up to here, it's 6 and 6. So what that means, of course, is that these two, this angle here and this angle here, are going to be equal, which is they're both going to be 45 degrees, right? Okay. So just sort of visually, you can pull a few things out of here and save yourself some time, going through and necessarily needing to write the equations to solve the entire structure. Okay. So at point A. So at A, you get 20 in the y direction. You're going to have 20 kNewtons going up, which is right here. Okay. And then it's FAL times 45 degrees is equal to 0. Okay. So, and you'll notice that the direction was drawn as being under compression, and that's why it's a negative here. All right. So what we find is that since it comes out to be positive, the direction was correct. So it's a compression. It's pushing into this point, which means also that at this point, at point L, it's also pushing into it. Okay. All right. The next thing we'll do is we're going to look at in the x direction. Okay. Now in this case, what you're going to find is we have potentially we have a reaction in the x direction, right? But what you're going to see here is that a of x, as far as this whole structure is concerned, is going to be 0. There's going to be no reaction in the x direction here, okay? Because this is on a roller support. So the only reactions that could possibly be in the x direction would be something over here, something over here. This has no reaction in the x direction, so it's just ax equal to 0, okay? All right, so now what that leaves us with is just this in the x direction, okay, which is this, FAB, and then the x component of FAL, all right? So this gives me the x component of FAL, and here's FAB. And it's negative, of course, because it's going off to the left, the negative x direction, okay? So now we have FAB, all right? So continuing on. Now we're going to go to joint B, all right? Now, if you look at this, you'll find that this is one of those zero force members, right? Because there's, and you can think about it too, it's like there's nothing pulling down here, right? And this gets free to pivot. So this is not providing any force to pull down over here, all right? So this one is going to be a zero force member, all right? LB. And it's only in the y direction, so it just comes out to be 0, all right? The next thing we will look at is what we're going to find here, of course, is that now there's only these member connected here. So essentially all the forces straight along this line. So at B, from B to C, it's also going to be 20 kNewtons. All right. So we already got FAB, but B to C is also 20. Right. And that's what we've come up with here. And it's under tension. And why is it under tension? Well, it came out to be positive, and we had it drawn off to the right. Right. So it's just you're going step by step to each joint. Okay. And the textbook solution goes to B first. The next one will go to L. Right. So at L, FLC. Okay. So now you have potentially force acting off in this direction. Okay. And in the x direction. So in this case, in the x direction, it's defined a little bit differently. Okay. Now you can always do this when you're looking at a specific joint. And the reason the textbook solution went like this and decided to go X like off in this direction was because what you'll recognize when you do that is you're going to have something that's perpendicular to it. So along this direction, defined as X, um, it might be better not to define this as X or Y here because it might get it confused with the others. But if you just call this like summation of the forces and you draw the arrow in that direction, it's good. And the same thing here. Maybe don't put a Y there, but draw the summation of the forces in the Y direction. So when you make this one of your axes, and this the other one, LC is the other one, what you'll recognize is there, because this was a zero force member, this is gone. So what you'll recognize here is that this is not acting at all to provide any force on this member here, okay? So this one also becomes a zero force member, okay? C, FLC. And that's what you come up with. You could also have done it where you could have, you'd done the angles and then try to figure out the X and Y components, but recognizing that this one's gone and you could have solved for it, but that would have taken longer. This worked out really nicely. Okay, so then in the Y direction, so straight along this line, well, there's nothing else there except the 28.8, which we already found previously up here, right? FAL. It's going to be the same thing, 28.8 minus FLALK. Reason is because this one was drawn in the negative direction of this Y component, whatever is defined as Y here. Negative direction, and this one's in the positive direction. So FLK is just going to be equal to 28.28 kNewtons. And it's compression because it's positive. The answer came out positive, and it was drawn as a compression. Okay? All right, moving along. Now we're going to go at joint C. Okay? So joint C, what we recognize, this is gone. This one's gone. So these two are zero force members. They're not even in the equation anymore. Okay? So now all we have is BC and CD, right? Connected straight across. So FCD minus 20. Why? Because BC was 20. Minus 20 because it's drawn off. Here's the diagram for this one. Drawn off to the left, so it's negative. FCD was drawn off to the right, which is positive. So there you come up with FCD. Now FCK, you'll look at FCK, so going from C, going up. What you'll recognize here is that there's just this 10 kNewtons going down. And then this must, as far as point C is concerned, this is a reaction pulling this back up. And what we recognize, these two are zero, right? So those are, if you redrew it and took these two out, that would be good. Okay? So now that's FKC or FCK here. Okay? All right. So the next one is joint K. All right. So we'll go back up here. We're now looking at joint K. So we have something going down here, pulling down, right? We already saw that. So that's pulling down, or in this case, we drew it as FCK going up. So this is compression, right? I'm sorry, this is tension. This is pulling up. This is also pulling down, okay? So that's that's for the Y component. Oh, well, this one actually the author drew it a little bit differently, or the solutions are a little bit different. Okay, so just looking at this is a little bit different at point K. And now the solution in text, they decided to go through this and do it as, here's one of the axes, and we'll look at that one first. So here's the 28.8, and then, I'll talk about this one, but I probably would have done it differently. So this is, I'll tell you what, we'll do this one first. We'll do this one first. Summation of the force in the x direction. This should be an equal sign equals 0. Okay. So it's 10 sine of 45. So the 10 was this one. Okay. And the reason we're making it sine of 45 is because we're trying to find the component that's along this line. Okay. All right. So here's the angle, the opposite side of okay, going back to the summation of the forces in this defined x direction should really just be an arrow plus an F instead of doing x because we've already defined these other ones. It might get to be a little confusing. But as far as this joint is concerned, we have the two directions. We have a component that's acting in a certain direction, and then something else that's off by 90 degrees or perpendicular to that. Okay. So here's our 10 sine of 45. Okay. So the way to look at this one is think about, okay, these are my axes. This is like my x, and it's like how much of this is projected onto this. Okay. So the angle here is 45 degrees. So the sine of this one, this should actually be cosine of 45, but it comes out to be the same. Okay, so it's like how much of this is projected onto this actual axis right here, x-axis. Okay, cosine and sine, the answer comes out the same. Okay, the next one is we're going to try to get FKD. How much FKD is projected on this defined x? Okay. Now, of course, when you've gone through this, you might have done this a bit different than this, but this is a solution, and since this is the one that's given, I'm talking through this one. So this is negative in the negative direction, and the reason is because it was drawn off. FKD was drawn off to the left, so FKD is this one right here. Okay. And now the only thing we wanted to do was find out how much of this angle is between here and here. So through trigonometry, you can find out that this angle is 26.5 degrees. Okay, so it's just going to be this whole angle from here to here is 45. So it's 45 minus 26.5, which leaves this little angle here left over, which is like 13, oh no, what, about 19 degrees. Okay, so you could solve for that, FKD. Now you have FKD. And like I said, this is one approach. All right, so the next one is the y direction. What's defined as the y direction after you've drawn these forces? Okay, so you have four potential forces here. All right, 28.8 acting off to the right, it's positive. 10 times cosine of 45. It's actually, this should be the sine because the angle's right here. It doesn't make any difference, at least the way I'm looking at it. It's a negative cosine 45 degrees. So it's how much of this is projected on this line. Okay. That's what this represents. All right. So cosine, yeah, it also works if you're looking at it from this perspective. Sine and cosine would give you the same. Depends upon which angle you're looking at. All right. The next is the 7.454 of FK. Okay. So that's this line. We know the magnitude of this line. And the sine is going to be like taking so you're thinking about how much like this component right here of this line, right, going along this direction. So the angle right here is the 45 minus 26.5, about 19 degrees here, and it's off in this direction. So, oh, sorry, not off in that direction. It's off to the right. So it's positive, okay? This component would act off to the right. And then minus fjk because that's going off to the left from what's being defined as positive. This is positive in this positive direction. So you can solve for that, fkj. Okay? So now there's one left. And the last one is going to be at joint J, right? So at joint J, you're going to have, let's see, we're going to have the two things. So we have something in the y direction. You're going to have this joint, this member, and this member going straight down. Okay, and the x direction. Oh, so the x direction was done first. Okay, so x direction, we're going to have an x component of this one and the x component of this one. Okay, so we're going to have, so it's 23.57 sine of 45. And what you'll recognize right off the bat, oh, of course, whatever, it's the sine is sine of 45 because the angle is the same. It's still the same up here for this large triangle. Okay. And the FJI is also the same thing. If you drew it off and you'll see the diagram here, it's at 45 degrees also. Okay. Well, we would have expected it to be the same magnitude as the, FJK is the same as FJI, right? Because of symmetry. So that's 23.57. And then in the y direction, what you're going to find is now you're going to have two of these. These are essentially the same, right? We already said that FJI equals FJK. So it's really like FJI plus FJK, both the same value, times the cosine of 45 degrees. Okay. So now you can use subtract out FJD, and that's equal to 0. So FJD equals 33.3. Okay. Now, due to symmetry, we did half of them. We did the half. We did the left side over here. And we had these two zero force members. And now what we can do is we could just use symmetry and substitute for everything else. Okay. So we already had half of them. And then we just come up with the other half. And zero force members are the same, of course, on the other side. And then, CK is EI, right? So CK is the same as EI over here. JK, we did those, KD and ID. So KD is the same as ID, okay, due to symmetry. And that's it. That's the end of this particular problem. Took a little bit. You might want to do this, you might not. This one got to be, I think, a little bit more complicated. Maybe you'll see it easier than, when I originally looked at it. I thought, oh, what? Maybe they're overcomplicating it. The only recommendation I would say is I don't really like putting it as like summation of the forces in the x direction and y direction. I would just leave these subscripts out because this contains enough information to tell you the direction and the sense, either it's positive or negative. Okay. All right. So that's it for that one.